So, yeah, basically this does not have a bounded derivative because as x gets close to 0, this fraction blows up. The way you can make it formally precise is you could create a sequence, for example. You could say something like if xn equals 1 over n, right, then the derivative of f at xn, actually let's make it 1 over n squared just to make it really simple. Then this becomes, the derivative becomes n over 2, right, which is clearly unbounded. Let me say it goes to infinity. I won't dwell on that. Okay? So that's not a bounded derivative on that. Okay, so the converse of corollary 5.4 is false. We good with that? We all right on that problem? Okay, if everybody's happy with that, then let's go on to problem 3. Guess I'll come over here again. Problem 3 is really just practicing derivatives here a little bit. So we take f of x equal to, it's piecewise defined, it's going to be x squared times the sine of 1 over x if x is not 0, and it's 0 if x is 0. Okay? And what I want you to calculate is, I want you to compute the first derivative of f and the second derivative of f at whatever points they actually exist. Okay? Any thought? Let's just talk about the first derivative first. Any thoughts on the first derivative of this function? So if pressure was on and somebody said, find the derivative of this, right? You're not in Math 350, you're out on the streets somewhere. Somebody says, find the derivative of this. What are you going to do? Besides, call me on my phone. Pardon?
Find it, product, and just a product rule.
So you're just gonna take this thing up here and you're just gonna use all the rules that you can, right? We have obviously a product here. We also have a quotient.
Yeah.
We have chain rule because the sign of an inside function. So all of the derivative rules, right? Now that applies for the non-zero values. So as long as x is not 0, we don't have to look at the bottom line, because if x is not 0, right, then I can create a neighborhood. Remember, really the definition of the derivative is it's a limit. As x approaches this point, maybe I should fix this point, like x naught, right? So as long as you choose your delta to be small enough that you stay away from 0, you never even have to look at the bottom line of the function. So you're really just looking at the top line of the function, and in so doing, you're working with functions that we've already established derivatives for. We don't have to rederive things. So let's just do that. So for x not 0, right, f prime of x, I'm just going to use, I think in the problem class yesterday I actually broke it down and I actually did the quotient rule and then did the chain rule and all that stuff. Let's just be a little quicker about it today because it dragged on too long. So the first term is x squared, and then the derivative of sine of a blob is cosine of whatever the blob was times the derivative of the blob, which we all know the derivative of 1 over x is just negative 1 over x squared. Plus, then we take the derivative of the first term, which is 2x, and multiply it by the second term. Make sense? Are we good with that? Okay. Actually, this simplifies a little bit. I will go ahead and do that. One reason to simplify it is that there is an issue of the second derivative here, and so it'll be easier for us if we simplify it first. So the second term is the positive term with the plus sign in front of it, so I'll use that first. And then here I have a minus, I have x squared on top and bottom, so I'm just going to get that. That's my first derivative. Okay? That's for non-zero x's. And I think I'm going to let you guys do the second derivative for non-zero x's. It's the same thing, you just take the derivative of this again. Okay, so we don't need to go over that. Let's talk about 0. And actually, yeah, let me just, okay, I'll just call it x or c or whatever it is. It's like a fixed point here. So how am I going to evaluate the derivative of this function at 0? Right. Just have to do it from the definition. Yeah, we're just going to do it from the definition. So let's write down what that would be. The limit definition would be x approaching 0, because that's the point we're evaluating. And I guess I'll just use the original definition, which was f of x minus f of 0 over x minus 0. There's an alternative formulation of the limit definition, but I think this is just going to be fine. Okay? F of 0 was given as 0, and so I can simplify this quite quickly. So this numerator is just f of x, which is just the top part, because x is not equal to 0, so I'm just evaluating the top line. And so I'll just get x squared sine of 1 over x, and then over x. So I'll cancel one of those x's with that. I'm kind of skipping steps here, skipping the details, if that's okay. I just get the limit of x sine of 1 over x. Okay. Anybody know what that is? Oh, I know what it is. It's just, this is a product, right? So, isn't it just the limit of that one times the limit of this one? And, oh, this one doesn't exist. As we talked about in class, we did an example to show that, right? Using sequences that converge to 0, but the sine function bounces from -1 to +1. So this limit doesn't exist, therefore the whole thing doesn't exist?
No.
Yes, you guys caught me on it. Yeah, I can't say that because it's only valid to split this into two limits if both individual limits exist. So if the limit on the right doesn't exist here, this doesn't exist, then what I just did was not a legal step. So I gotta back up, I can't do that. And even if, let's say that, let me give you another idea. Let's say we know that this f prime of 0 does exist, right? I don't know what the value is, but let's suppose it does exist, and then I say, well, then if it does exist, sort of by way of contradiction or something, if it does exist, so this is f of x minus f of 0 over x minus 0, if that does exist, can't I just write it as, what am I trying to do here? No, sorry. So let me just ask you this, can I do this? Limit of x sine of 1 over x over the limit of x equals the limit of sine of 1 over x. Is that valid?
No. If the top limit exists.
Let's say it does. Let's say that this top limit does exist. Actually, it does exist, as it turns out. It does exist. So this one exists, and this one exists. So then, does that mean that this one exists?
We can only use that if the limit of the bottom one is not 0.
Right. Only if the limit of the denominator is not 0, which this is 0, would this have been valid. So this is also not good here. Be very careful with using that proposition about products of limits and sums and differences of limits and stuff. Because there's lots of ways to make mistakes, especially with division and multiplication. So I'm going to back up. We can't do any of the things I've been saying. Let's go back to this limit. Anybody have an idea about that limit?
The squeeze term?
Yes, I like that. So what do you want to squeeze and how do you want to squeeze things?
Well, we know that the sign of 1 over x is between 1 and -1.
Okay, great.
So if we multiply x to that inequality,
Okay. Like that.
we could say
I suppose that's for positive x's.
yeah.
Yeah.
And since we know that negative x as the limit as x goes to 0, it's
Mm-hmm.
going to be 0, and it's the same thing for that one.
Mm-hmm.
Then that means that.
There you go. There you go. This limit equals 0. Okay? So this equals 0 by the squeeze theorem. By the squeeze theorem. Okay? Does that make sense? Awesome. And here's the squeezing that's going on right here. Okay, perfect. Yeah, another way to do it would be to just look at the absolute value of this, right? And notice that that's less than or equal to the absolute value of x, but obviously it's at least 0. And so then you've got this going to 0. This one clearly goes to 0. Therefore, the absolute value of the function converges to 0. And I think you did prove in a homework assignment that that means that the function itself converges to 0. The only reason I slightly prefer this over this one is on this one I have to be careful that x is a positive number, because if x was equal to -3, you'd have 3 less than or equal to something less than or equal to -3. And that would be nonsense. Basically the whole thing is flipped the wrong way around. So you almost have to, but see, technically, you're taking a limit at 0, so you're taking a neighborhood that includes some positive and some negative values. So now you've got to consider both cases. I just prefer to just avoid doing cases by taking absolute value here. At any rate, so this limit equals 0. So the derivative of the original function at 0 is equal to 0. Okay? What about the second derivative at 0? At any non-zero value, I'm just going to take the derivative of this. So the second derivative at 0, this is going to be, by definition again, the limit of f prime of x minus f prime of 0 all over x again. And we just calculated f prime of 0 to be 0. So this is just the derivative of the function, well I guess that's right here, right, divided by x. So this is the limit as x goes to 0 of 2x sine of 1 over x minus cosine of 1 over x all over x. Okay? And that's what we have. Any thoughts on that limit?
Can you say that one doesn't exist?
This isn't going to exist.
Because of the 2x, it would cancel, right? So you just have 2 sine of 1 over x for part of your limit?
Yeah, well you have 2 sine of 1 over x here in the first part.
That doesn't
Okay,
exist.
that doesn't exist. Now, what about on the second part here? Let's see, cosine of 1 over x, and it's going to be one of these highly oscillating things, and it's going to get damped by the, actually, no, it's going to essentially, actually, the second part is going to more or less just blow up. Right, because cosine is going to be between -1 and 1, and as x gets close to 0, this part's going to explode. So you have one piece that's exploding, you have another piece that doesn't exist. Here's the thing, you got to be a little careful, because you could have the two parts both not existing. And somehow, after you add them together and combine them, magically, it could exist. So I don't want to be too quick to say, well, just because the first part didn't exist, the whole thing doesn't exist. We can't really say that. But it's mainly because, all right, both parts don't exist, but they don't exist in different ways. The first part is just an expression that's bouncing between +1 and -1. The second expression is blowing up to infinity. So what you could just say is that this expression is unbounded. It's literally unbounded. So in other words, if I were to sort of break this up, it would be 2 sine of 1 over x minus cosine of 1 over x over x. That is just an unbounded expression. So let x approach 0, right? Then this part will be bounded by 2, and this part will become arbitrarily big. So it's unbounded. So it doesn't exist. Unbounded as x approaches 0. Okay? Incidentally, let me just ask a follow-up question that's not on the handout. Is this function, uniformly continuous on, what domain do I want to use? What domain did I use when I did this yesterday? Do you remember, Asha and Joseph? That's the follow-up question on uniform continuity.
I think I had
0 to 1, right? Oh, okay. All right, I'll let it just make up the question then. So is f uniformly continuous on the closed interval 0, 1? What do you suppose I'm getting at with my question? Why would I be asking you that? Yeah, we just calculated the derivative, right? So, and we've been talking about that corollary. If the function has a bounded derivative on some domain, then it's uniformly continuous on that domain. So here's our domain. Is this expression bounded on this domain? Pardon?
What cosine between 1 and 1?
This is between -1 and 1.
That's between
-2 and 2.
So-
-1 and 1.
Yeah.
Doing a subtraction. So what's the absolute biggest this could ever be if you really were liberal about what it could be? 3, right? 3. It can't actually be 3 because you can't have this part equal to 2 at the same moment that this part's equal to 1, or -1, I guess. But as an upper bound, you could just use 3. So the answer is yes, by corollary 5.4. This makes some very good test questions, actually. Part A is find the derivative, and then once you've done that, then part B is to ask this as a follow-up. If you see those questions in succession like that, you should be thinking about this corollary, because it's probably, I asked those questions in that order on purpose. So, make sense? Okay, great. I'm going to be out of room on my video card, so I'm going to go dump the video on my computer real quick and then start it up again for the next question. So the next question, while I'm doing that, it'll only take me like 2 minutes. While I'm doing that, you guys can start thinking about problem 4 on the sheet. So let's do that next. Problem 4, I'll write it down. Okay, so think about how to do problem 4, and I'll be right back.